Good morning, good afternoon, and good evening, everybody. With great honor, I am presenting today our speaker, Dr. TOMAZ CATUNDA, who obtained his undergraduate and PhD degrees in physics from the University of São Paulo, Instituto de Física e Química de São, in 1982 and 1989, respectively. He did 2 years postdoc at the Massachusetts Institute for Technology in 1990 to 1992. Presently, he is associate professor at the Instituto de Física de San Carlos. In 2008, he stayed 3 months at the University de Caen as is visiting scientist sponsored by CNRs. His main research expertise is optical spectroscopy of condensed matter physics with particular interest in rare earth doped photonic materials. He has been working with conventional, nonlinear, and photothermal spectroscopy. His main expertise deals with ground state and excited state spectroscopy of ions in solids, time-resolved spectroscopy, PROF experiment, thermal length, C-scan, energy transfer process among ions, and fluorescence quantum efficiency determination. He has advised 9 PhD students and supervised 9 postdocs. He is an author or a co-author of about 146 papers in peer-reviewed journals. According to the Web of Science, Dr. Catunda has more than 3,715 citations and impact factor 33. Now, I would like to invite Professor Catunda to deliver his talk. Please, Professor, you are welcome.
Thank you, Humberto. Good day to everyone. Thank you for being here. It's a great honor to be here today. I thank all the organizers, particularly Professor Sankara Rama, Humberto, and also Dr. Swapna. So the topics of my talk, the title is Refractive Index Change in Spectroscopy of Ion Doped. Outline of the talk is the motivation for the study of thermoelectronics refractive index changes in photonics materials. I will start with thermal lens and ultra-sensitive absorption, and temperature dependent of thermo-optical properties, measurements of fluorescence quantum efficiency, and then I will go to the electronic refractive index change in higher doped materials, some results using the Z-scan technique in ion doped neodymium and chromium materials, some results in terbium doped materials, and conclusions. So, the laser was first realized in 1960, so long time ago. And the main features of the laser is the monochromaticity, spatial coherent, and high intensity. So all these main features are affected by disturbance in the cavity, namely thermal lens or refractive index change. Okay? So they are crucial to the quality of the laser. So a few years after the first operation of the laser, it was realized that the problem of optical distortions can virtually preclude diffraction limit laser operation, even if the materials themselves are diffraction limit of optical quality. So now thermal lens is a chapter, an important chapter in laser engineering, and so, but also we have in ion doped materials, we have the question of a thermal refractive index change. They appear in some circumstances. I will show some, mention just some of them. You have a standing wave in the laser cavity that gives rise to a modulation of the excited state population. and this gives results in a modulation of the refractive index. Okay, was first observed experimentally using a light-induced grating experiment. And also you have the effect of the changing refractive index during the laser pulse gives results in a change in the frequency. So this was first understood by Paul. The frequency drift is due to the inversion depends on the change of polarizability of actually it's the chromium ions in ruby. Okay, so when the ruby goes to excited state, you have a change in refractive index because the polarizability of the chromium in the excited state is different than the polarizability in the ground state. This was also studied by in another paper in neodymium doped glasses, and the same the main conclusion is that you have also in neodymium doped glass you have a metastable state, so you have a population of the excited state. That is the population of the excited state results in a refractive index change which is proportional to the excited state population. So it's also an effect of the refractive index polarizability difference. And today you have very big lasers like the one in the National Ignition Facility. You have very sensitive and very big experiments. Just to give you just two examples, like the laser interferometer for a gravitational wave. And so we need to monitor, to study very carefully the optical materials, the passive and active optical elements in your laser cavity. So photothermal spectroscopy and the photothermal techniques play an important role in this field. Like for instance, I'll show you some example where you can this photothermal common pass spectroscopy is actually a kind of thermal, it's a thermal lens experiment, a pump probe thermal lens, where you can, here in the left side, you can see that you can map the absorption along the sample by scanning the sample position in the order of 10 to minus 4 centimeters, like here also another result from Germany in lithium niobate. So all these optical materials, the laser, the active materials, like lithium niobate is frequency converter, and also the thin films, everything can be studied with photothermal spectroscopy. About the thermal refractive index exchange, we have effects on the laser behavior that's in our textbooks, but you have also applications that are still a challenge, like phase conjugation laser or coherent beam combined. So if you want to combine several, for instance, fiber lasers, very high power fiber laser, want to combine with good optical quality in order to keep the coherence, spatial and temporal coherence, so you can use these ideas of phase conjugation. But that is still it's not very popular because you still don't have very good laser materials with very good nonlinearities. So this is what's the motivation. So I will start with an example of application of thermal lens in ultrasensitive absorption. So for those who doesn't know, the effect of thermal lens is that you heat a sample and then you have the transverse diffusion of heat that gives rise to the distinct temperature profile shown here. So you have an increase of temperature in the center of your beam, and also a spread of the heat transversely due to heat diffusion. So your temperature change is proportional to the absorbed pump power and inversely proportional to the thermal conductivity of the material. And also the response time of this your thermal lens effect is due to the response time of the heat diffusion is given by this factor Tc, where W is equal to W squared divided by D, where D is the thermal diffusivity, which is proportional to the thermal conductivity. So in a typical experiment, you have a thermal lens transient, like here in a CW experiment, a pump probe. And so you have two parameters that you fit this transient. One is theta. This theta is proportional to the amplitude. Okay, it's proportional to the absorbent pump power divided by the thermal conductivity. So these factors is actually proportional to the temperature, laser-induced temperature change. So, so what we actually have here is something proportional to delta T, the temperature change, times the NDT. This is a refractive index change. So actually, what we are doing in a thermal lens experiment, we are doing you could call this single pass interferometry. That's and so the sensitivity you have is comparable to the interferometry. But here we have a single beam interferometry, so where delta, this phase change is the phase between the center of the beam and the border, the wings of the beam. Okay, in this case is an example of where we did measurements in pure water. So so we have a signal, relative good signal to noise with a signal that is less than 1%. And you can, so by measuring this parameter theta, you obtain directly the parameter, the absorption coefficient, and you could estimate the temperature change is about 10 to minus 6 degrees Celsius in this example. So, so the first example I will give you is the question about spectroscopy of water. So you see that water is obviously a very important material, optical material as well, but it's remarkable that the absorption coefficient change 11 order of magnitude in the UV, and it has a minimum absorption in the visible in the blue, and it has been studied in the last decades with different techniques, particularly the photothermal techniques in red here, so different authors. So it's with the time absorption is becoming smaller and more shifting to the blue. So this is this red stars are our measurements using photothermal spectroscopy. And you reach about 2 times minus 3 inverse meters. And this work was done in collaboration with Dr. Marcano, who visited me. At that time, Dr. Cabrera was still a student, so it was some time ago. And so it was later, so our points are here in red, so our more recent experiments appear almost 10 years later, so they are not very different from ours. But this is experiment, this green result, points here are experiments made in Texas and by Professor Fry. The group is a specialist in the subject, and it's very complicated. Interrogation cavity measurements are very much more expensive and sophisticated device than ours. So the second topic of this talk is the use of thermal lens to study thermo-optical properties of some materials. I'll show an example in neodymium YAG, where we compare neodymium YAG ceramics with neodymium YAG single crystal. So here's a picture of it's quite large, it's 10 centimeters per 10 centimeters slabs of ceramic. And so the spectroscopic and optical properties of the ceramics are nearly identical to the ones of the single crystal. But you have here, show here in the right that you have 2 microns, about 2 microns microcrystals. And here we use thermal lens setup to measure the to investigate here at first at room temperature to investigate the thermodiffusivity. So at room temperature, it shows that the thermodiffusivity of ceramic in single crystal are very similar, but at a low temperature, about liquid nitrogen temperature, the signal with the ceramic is lower. So it means lower thermodiffusivity, and this was observed as a function of neodymium concentration. So you see that at low temperatures, we have the ceramics behave very different than the single crystal. And this is related to the fact that at low temperatures, the phonon mean free paths become longer, comparable with the size of the microcrystalline ceramics. This work was done in collaboration with colleagues, with Carlos Jacinto, my former students, and Benayas and Jacques from Madrid. Okay, so next topic is fluorescence quantum efficiency measurements using thermal lens. So all the photothermal techniques have been used to measure fluorescence quantum efficiency, photoacoustic, calorimetry, etc. And the main idea is to determine from the photothermal method, instead of determining measuring the light that comes out from the material in order to obtain the quantum efficiency, the idea is to measure the heat efficiency, the fraction of heat that results from the absorbed pump power. So in order to obtain the quantum efficiency, which is defined as the fraction of emitted photons divided by the absorbed photons. So now general photothermal experiment, if the quantum efficiency is 0, this at heat is 100%. Every absorbed power results in heat. If the quantum efficiency is 100%, then you have this term at heat is given by the quantum defect, the difference between the emission energy in red and the excitation energy. So this parameter is also called quantum defect. Now, general case, if you know the emission frequency and you determine the photothermal parameter heat efficiency, you can obtain the quantum efficiency. Okay, this term, the ratio between the emission and the excitation frequency can also be written in terms of the excitation wavelength. The first example I present here is a neodymium YAG, and so what you see here is that the thermal lens signal divided by the absorbed pump power, that is this capital theta parameter, it decreases linearly with the excitation wavelength. That's because as you increase the excitation wavelength, you decrease the amount of heat that you are depositing in your material, and you are also decreasing the quantum defect. So here we are assuming that every place you excite here in this line, because we know the spectroscopy of neodymium YAG. So everywhere you excite, it's going to decay by phonon very fast to the metastable level. It's about 200 microseconds. So this process is very fast. So the excitation wavelength and the quantum efficiency doesn't change. We know that the quantum efficiency doesn't change in different excitations, and you see this result corroborates this hypothesis. So from this straight line, you have two parameters. Obviously, So one part, this is related to this equation for capital theta here, where you have the quantum efficiency is related to the slope of this curve. In this case, we obtain 95%. And also this constant here, that is the second parameter, is related to this the thermal conductivity, the probing wavelength, and the SDC, the change of optical path with temperature. And in this case, it's about 14 10 to minus 6. It's close to the expected. So just to remark that, so the SDT is given by the NDT, but also things related to expansion and stress. Okay, this parameters. Also, you can use the thermal lens spectroscopy using tunable lasers. You can do spectroscopy like any technique. So here, what we expect here, what we see is that the thermal lens spectrum just resembles the absorption spectrum as you would expect for this material. Because again, because everywhere you pump here, the quantum efficiency is the same. So the excitation spectra is the same as the absorption spectra. Another result that I think is interesting is to do the thermal lens experiments inside the laser cavity. So here we have a neodymium laser again. This was this case done in collaboration with our colleagues from Madrid. And so you pump at about 808 nanometers, and you have your cavity, you have your laser crystal here, and then you use a probe beam inside the cavity to probe the thermal lens inside your material. And what you observe here in the right is that when the cavity is misaligned, you don't have a laser emission. You have a higher signal than when you have lazy. Okay, in this case, so you have a decrease of your thermal lens signal with the laser operation. That's because from this equation here, we increase the heat fraction, because we increase the quantum efficiency. So the quantum efficiency, effective quantum efficiency, when you have laser, it goes to about 95% to 100. So the quantum efficiency here in this case is about 90%. Without laser, it goes to 100 because the stimulated emission increases the effective quantum efficiency of the system. Okay, so here in the right side, I have the results at 106.64 nanometers. You have the decrease of the thermal lens signals with the laser operation. However, in the left side of this view graph, you have the results at 1340 nanometers, 1.3 microns. And here, the opposite happens. When you have laser operation, you increase the heat release, you increase the thermal lens signals. That's because when you have lasing action at 1.3, your cavity is forcing the system to emit only at 1.3, where the energy is lower. So you have a larger quantum defect. You have, in this case, the thermal lens signals increase because you are decreasing the emission wavelength. Okay? And all these results are consistent with our previous results, the thermal conductivity, the quantum efficiency, etc. Another experiment, just to show you the same idea. So here in the half, the same idea, main ideas with the terbium doped materials, which are very important because very very low quantum defect, the difference between emission wavelength in these cases and absorption wavelength is very low. It's about 3% quantum defect. So you see here in your left side, you see the photothermal spectra using a tunable Ti-sapphire laser, about 900 nanometers, is almost identical to the absorption spectra. However, to do the experiment, you just divide the photothermal spectra by the absorption spectra, and then you have this parameter capital theta here. And then you have, when you divide these two similar curves, you have a nice straight line. And here you see, so this decrease of your photothermal signal with the excitation wavelength is the result of decrease of the quantum defect. And so we are decreasing the heat release. And from this, the slope of this curve, you get the quantum efficiency of the material. So you have a study many crystals, glasses doped with several rare earth and chromium doped materials, and there are a lot of process, quenching process, energy migration, effect of impurities, effect of OH. We did a lot of studies in these materials using the thermal lens technique. Also, another study here in core shell quantum dot solutions. We have so we have this core shell CDSE zinc selenide cadmium zinc sulfide cadmium selenide quantum dots, commercial quantum dots in organic solvents. This is in a liquid, it's in a COVID. So you have here first in the right side, first open, you have the photothermal signal compared with the absorption spectrum. And then when you divide this capital theta is the photothermal signal divided by the absorbed by the absorption. So it's normalized by absorption. We have again, like previously, a straight line, okay, and here, so with this straight line, you obtain the quantum efficiency. Actually, I like to remark that there is there are several ways to do, but here we compare two different methods. One thing you could do is we don't need to do all the scanning frequency and the excitation, because if you know this constant C here that is related to the NDT, in this case of the solution, or if you know the thermal parameters of your solution, you can use it as a reference. So you can obtain the quantum efficiency using a single excitation experiment. But you do need to have this constant thermal optical constant. So you have in this case we did with two different methods and obtain a reasonable agreement about 80% quantum efficiency. Okay, so now I will start the subject of electronic change of refractive index. Refractive index due to electronics, this effect is not a thermal effect, and in higher doped materials. Okay, so here what is soon realized in the first experiments is that this polarizability difference. So as I mentioned before, you have a refractive index change because you excite a metastable level. And you have a significant excited state population. This excited state population results in a refractive index change due to the difference of the polarizability between the excited and the ground state. So if you take, for instance, neodymium, and do the experiment in different hosts, like glasses and crystals. You have about 1 order of magnitude change of this polarizability difference with the host. The same ion in different hosts. So you have oxide, for instance, YV4 here at the top in your left graph, and this is 1 order of magnitude higher than fluoride crystals. Similar experiment. This was done in the left side was done by very important laser scientists, Paul and Steve Payne. This was done in Livermore. And in the right side, you have was done in the group of Professor Richard Monconger with collaboration of Professor Antipov in Russia, and was the subject of a thesis where they also studied the dependence of this polarizability difference in different, in this case in France. Also, they have a crystal here, so we have this. They study neodymium and thermal doped materials. And so how we from all the experiments, you know that there is significant change in polarizability with the host. So it's a parameter that could be understood. It appears to be interesting for spectroscopy because it's related to the environment of your crystalline field. Also here I put I put this polarizability. It seems to increase inversely proportional to the band gap of the crystalline host. So it's very related to the properties of the host and how the ion interacts with the host. Okay, so the understanding that we have today, more or less common in the literature, is that you have for people who are familiar with the spectroscopy of hard earth ions, we have the F to F transitions, which have low oscillatory strength and are forbidden by dipole forbidden transitions, and which are responsible for most of the emission in the red of the hard earth ions. But also have transitions in the UV, which are dipole allowed, have much larger oscillatory strength, but are far away in the UV. And so all the results, qualitative results, indicates that this 4F, the 5D levels, are the ones which are important to determine the size of delta alpha. That's the reason why the polarizability changes delta alpha is larger in oxide than in fluorides, because in fluorides, the 5D level are much higher energy. Also, an interesting result here is that we measure this polarizability difference as a function of the temperature in an oxide crystal, but it's a crystal that has a phase transition from ferroelectric to paraelectric. And here, what is you see here, open circles is the changing in absorption, but here is full circles is the changing polarizability. So you see that polarizability parameters, this delta alpha, it changes 1 order of magnitude from 0.12 to 0.2, okay, along the phase transition. And what is, I think, is a remark. So it's very sensitive to the environment of the ion in the crystal. And what is remarkable for me is that the lifetime, because the lifetime of the neodymium ion is also determined by the environment. That in this experiment, the lifetime doesn't change, almost doesn't change. The change in lifetime is almost negligible through the phase transition. but you see that the polarizability is very sensitive to the phase, this phase transition. Okay, so now I'll show you some examples of the Z-scan technique, which was, the technique was invented many years ago by Sheikh Bahrai and co-authors. Very popular technique. It's the same idea of the thermal lens, is that you have a modulation of the refractive, transverse modulation of the refractive index, in this case because of a nonlinear effect, okay? And this modulation of refractive index changes the intensity in the far field, okay? So here in this case, when you have a positive lens, you have first, as you scan the sample, you have a decrease in transmittance and then an increase. And then you have this typical Z-scan curve, okay? And where this change in transmission is proportional to the refractive index change, or the phase change. So this delta T, peak to valley, PV, in the right side here, is proportional to delta phi 0, where delta phi 0 is the phase change. In this case, the phase change between the center of the beam and the wings of the beam. So the idea is the same as the thermal lens idea, but the idea of scanning the sample is particularly interesting for nonlinear optics, where you use you pulsed lasers, so sometimes very fast, so it's difficult for you to measure transients, okay, like you do in thermal lens. But but the main ideas are the same. So we have been doing these kind of experiments in slow materials, where you can use a CW laser with a chopper. So materials which have a slow nonlinearity of about 10 microseconds or larger, you can study using a chopper. And then the idea is that the idea of the Z-scan is that by scanning the sample, the main idea here is that if you have no nonlinearity, you should have, in principle, no signal. So this is your reference, is your signal when the sample is far from focus in the right or in the left. Okay. So if you have a good apparatus and a good sample, you should have a horizontal line when you have no nonlinearity. So the problem with in reality, in real practice, your signal is limited by several problems in for instance, in the sample, the sample is not very homogeneous, or if the sample has some problems in surface and so on, and also your lasers. So here we do a double normalization technique. We do the Z-scan, but we also normalize in time. So when you are in the right side here at the top, when you are far from the focus, you have no nonlinear signal, you use the initial time here, Ti, as a reference for your measurement. So you always divide your result, you measure at initial time using computer acquisition system. You measure at the end of the pulse and normalize by the initial time. So you doing this, you get the Z-scan. So here in the left you have Z-scan from the original paper from Sheikh Bahai. So it's here they obtain good signals to noise, about 1%. Okay, that's not trivial to obtain using pulsed lasers. But here on the right side, you will obtain a sensitivity that is 2 orders of magnitude higher. So here the signal to noise is much smaller because by using CW laser in an ion doped material, you can, using this trick of initial time reference, we can have signal resolutions, signal to noise much about 2 orders of magnitude better than 1%. So I'll start with neodymium doped materials again. Here I'll show some examples show excitation at 808 nanometers. So what we have, remind you that in the this kind of experiment we have 2 detectors. One here in red, what we call closed aperture, has an aperture in order to select the center part of the beam, which is sensitive to the refractive index change, or the refractive index modulation, actually. In the right, what you call open aperture detector has no aperture. It collects all the light, so this is sensitive to the absorption. So here, the open circles, you have this curve where you have an increase of the signal at the center of the beam. This is a result of saturation of the absorption. Okay, and with the what I call here S2 is 100%, so it's the open aperture detector. The other detector, we collect 50% of the light. We have this curve in black, and by using the Z-scan recipient in order to separate the refraction and absorption, we just divide this full circle here, and then you have this triangle, this triangle curve here, and then you have the characteristic Z-scan curve. And then okay, then we have in the left side you have the characteristic Z-scan from which you get the real part of the nonlinear refractive index. From this you get the polarizability difference. It's about 10 to minus 26 in this case, and also in the right side you have this imaginary part of the nonlinear refractive index. In this case, you will obtain the difference between excited state absorption and ground state absorption. This difference is negative, meaning that the preponderant effect is the saturation of the ground state absorption. So we obtain this delta signal here, and also in this case, we expect the excited state absorption to be negligible, so we obtain the ground state absorption, which is comparable with expected values. We could also study the refractive index change, the dynamics, and you see that also here the closed aperture, you see the refractive index change. Open aperture, you see the change in transmission, and you have some saturation effect and you can study more in details or not. Go further in other experiments, that is to use pump probe and to spectroscopy. So here we have a pump probe scheme where you have excitation with an argon laser. In this case, it's a chromium doped material, so it goes to excitate, it relaxes very fast to the metastable level. And we are going to probe this refractive index change with tunable Ty-Sapphire laser. No, sorry. In this case is dilays. So, as similarly to excited state absorption experiment, what we are going to show you are excited state dispersion, because when you see the refractive index change you do the spectroscopy and see the change in refractive index, the spectroscopy of the dispersion of this refractive index change. So in the left side, you see the spectroscopy. So by scanning the dye laser, you see the two lines of the chromium absorption. This is about 69 nanometers. That was in chromium doped alexandrite. You have these two lines. So you have the signal here when you have absorption. So if I just compare these two lines, you see that they are very similar. Okay, they are very similar, but the close aperture is a little bit shifted, distorted. So what does the Z-scan recipes tell you? In order to discriminate absorption and refraction, nonlinear absorption and refraction, you have to divide this black curve, this red curve, divide by the black curve in order to normalize. Then you do this division, you get this very nice, you have this dispersion, okay, which is as we should expect it. So you have the dispersion, but you also have a background here. And above you have the saturation of the absorption that is similar to the absorption of similar to the linear absorption. Okay, so we did that here in neodymium doped crystals with a tunable here at 800 nanometers, 880 nanometers, and then doing the same thing by scanning the laser, we could discriminate absorption, this saturation of this absorption of this case as neodymium YAP is very similar to YAG, and you have also saturated dispersion. Here in the left side we have neodymium YAG. Okay, so here we see that you always have this dispersion curve on the top of a plateau. Okay, you have this dispersion in alexandrite in the left, in neodymium YAP, and so what about the Kramers-Kronig relation? So a lot of people use the Kramers-Kronig relation to calculate nonlinear refraction from nonlinear absorption. However, so this is given the idea is to use this integral where the refractive index you apply to the linear opposite, you apply also to nonlinear opposite. The refractive index change is also related to the difference in delta alpha. Here is delta alpha is the absorption change. Okay, the problem with this integral, this is very important in physics, very fundamental. The problem is that this integral goes from 0 to infinity. So we are as experimental physicists, we know that no spectroscopy measurement is made from 0 to infinity. So this gives rise to this plateau here. Okay, so this plateau is what you miss by not considering the contributions to the refractive index change, which are comes from the UV. So you have this resonant dispersion, you have this resonant absorption, you have this resonance dispersion, but this resonant dispersion is on the top of a plateau, and this plateau is due to these transitions in the UV, which are very important for the refractive index, to the linear refractive index of optical materials, but also to the refractive index change or the polarizability change. So we are not breaking or the Kramers-Kronig relation. We are just showing one example, but you have to be careful and in the application of the Kramers-Kronig relation. So so the last topic is results on terbium doped materials. The idea of terbium doped materials, terbium is very important ion for luminescence in lightning because of the green emission. at about 540 nanometers. But it has also for us interesting feature that the energy of the 5D levels are they have relative low energy position compared to other high Earth levels like neodymium or like lutetium or terbium. Okay, so this is going to be important. I will skip this. So here we show, I will skip this result because of the lack of time. This is a phosphate glasses where here we could discriminate thermal and electronic contributions. And so we shown that refractive index increase linearly with concentration, we obtain the polarizability difference. And I will focus our results in aluminum silicate glasses, terbium doped aluminum silicate glasses. The glasses were prepared in the group by Professor Baesso, whom I thank for 30 years of collaboration with my main collaborators, and who teach me to use the thermal lens setup and teach me many things. And I'm very glad he's here today. And what we have here is the specialty of Professor Baesso is low silica aluminum silicate glass. What's interesting here is that by changing the proportion between a calcium oxide and silica, you can change strongly the features of the glass. By increasing the silica, you improve your transparency in UV, we increase the band gap of the glass, and by decreasing the amount of silica, you decrease the band gap of the glass, and you improve not the UV transparency. Your UV transparency is poor, but you improve the transparency in the infrared. Okay. So what we did here was to compare two different kinds of glasses. Is what you call calcium aluminate glasses, which have higher CAS, have a high amount of silica, and low silica glasses. Okay, so the high amount of silica is high band gap, high band gap glasses. So we measure the polarizability difference. The signal increase linearly with the intensity as you would expect for, in this case, in terbium doped glasses, high silica aluminate glass. You have some excited state absorption, and your open aperture Z-scan, the signal decrease at the center because the absorption is increasing. And this is, we can expect that because you have the 5D levels in UV, and this is more or less comparable with the data that we expect. So we have an excited state absorption that the excited state absorption cross-section is much higher than the ground state absorption. However, when you go to the low silica glass, you have a non-linear behavior. You have a changing refractive index, which is parabolic. And this is, so here we are at low silica is a low band gap. So you have more excited state stuff going on. And here we see that you can interpret this curve as not only the effect of NE2, which is proportional to the intensity, but a second effect proportional to the square of the intensity. This square of the intensity is due to a second excited state. So you have the population of two metastable states. Here in the right, you have the 5D4, which is the one which emits in the green, and you have after the 5D3 with about 1 millisecond lifetime. So we have two excited states, and this gives rise to this change here that in the case of CAS here in black, you have almost no, it's almost flat, but this is LS CAS, which is lower band gap. You have this strong excited state phenomenon. So it's the first time that we see that change of refractive index in ion doped materials due to the second excited state. And we also did measurements in phosphate glasses, this low silica, high silica. We see that this terbium doped materials, terbium ion, is very extremely sensitive to the host. So it's more sensitive than neodymium or terbium or other materials. So you see that the difference we measure between calcium doped fluoride to low silica calcium aluminate glass is a factor of 50. So this is we believe it is a consequence of this low energy of the 5D levels of terbium. So as a conclusion, sorry if I'm a little bit late. So I think I will skip the conclusion to the time, and oh, sorry. Acknowledge my collaborators of many years, and thank you very much for your attention. And just announce that they have a possibility of one postdoc position, and we are looking for more people to work, and collaborators are always welcome, as well as students. So with that, I thank you very much for your attention, and thank you again for the invitation. I'm very glad to be here today talking to you.